The next problem is about linear approximation. So we want to approximate functions now, right? So consider the following. F of 1 is 4, f prime of 1 is 1. Use this to find linear approximation to f of x at x equals to 1 to find f of 2. So linear approximation means you'll use line or a linear equation to approximate the function. So now we know here f of 1 is known to us. F of 1 is 4. F prime of 1 is 1. And we want to find out f of 2, right? But we do not know f of x. We do not know f of x. So if we do not know f of x, the function, how can we find 2? All right. So we cannot know f of x exactly. So we want to find an approximation. Let basically justify the word linear approximation. So the idea is as follows. So you have a function. So let me draw a picture of it. So you have a function which goes somewhat like that. You know the function value at a. Not only you know the function value at a, you also know the tangent line equation at a. So at a, the point on your function is given by a comma f of a. And the tangent line will be given by, so this is your tangent line. So your tangent line is, so this is your tangent line. And what do you want to do? You want to find out, so this is known to you. So equation of this line is known. And what you want to do is you want to find out nearby, you want to find out if this is x, you want to find out f of x. So f of x is your question mark, but instead of finding f of x, you will basically take this value and this will be your what? Linear approximation. Yeah, so you can report that this point is close enough. Again, approximation is something in the head, right? I mean, like sometimes when you're doing, say you want to kill a bacteria or you want to see the boundaries of bacteria, you have to go really small, right? In nanometers. Yeah. But if you want to lay a brick on top of the other, nanometer difference will not make any difference. So the idea is approximation is something which is defined by the user or the person who's finding it. Some approximation be good enough, like say if you're dealing with billions of dollars, a 10-cent approximation is not bad. But if you're dealing with only say 20 cents, then 10-cent approximation is a bad approximation, or 10-cent error in the approximation is a bad approximation, right? So it depends on the scale of things you're dealing with. So now, so we are using the equation of tangent line at a comma f of a to find out approximation for x. So let's see how would we go about it. So what is the equation of this tangent line? The equation of tangent line at a comma f of a is going to be what? Is y minus f of a equals to f prime a times x minus a. Of course, if you're using a to approximate for x, then the tangent line better exists there, right? Otherwise, this whole apparatus will fall apart. So that means the function should be differentiable at that point. Or we get y equals to f of a plus f prime a times x minus a. So see, what is your f of x? F of x is your y value, right? So instead of finding the function f of x, you're finding the value of you're finding the value of x on this tangent line. So let's call this as L of x. So you are finding, instead of f of x, you're finding L of x. Okay? So this is the linear approximation. So let's try to formalize this now. A linear function L of x, which came from here, f of x plus f prime a times x minus a, is called linearization of f at a, because you are basically approximating it by a line. And if x is close enough to a, then f of x is roughly L of x. You can see L of x value is here. This is your L of x value. This is your f of x value. And then you can report that they are close enough if x is close to a. Right? The closer you go, the closer these values will be, right? So if we have x close to a, then we have f of x is roughly equal to L of x. So this is approximately equal to symbol, which is f of a plus f prime a times x minus a. So this formula, or this approximation, is called linear approximation of f at a. All right. So let's use this to do our problem. Now we are using what? So let's read this. F of 1 is 4, f prime of 1 is 1. Use linear approximation to find f of x at x equals to 1 to approximate f of 2. So here a is equal to 1, right? So we have f of x is roughly equal to L of x. This part is the linear approximation part, right? You're approximating f of x by this linear function, hence the name linear approximation. And that is equal to f of 1 plus f prime 1 times x minus 1. Now, what do we get? L of x. So therefore, we want to find f of 2. So f of 2, let's first find L of x, right? So L of x is going to be f of 1, which is 4, f prime of 1, which is 1, x minus 1, which remains as it is. So you get 4 plus x minus 1. So now what is your f of 2? Your f of 2 is roughly equal to L of 2, which is going to be 4 plus 2 minus 1, which is 5. So thus you get f of 2 is roughly equal to 5. So again, now use linear approximation to find approximate square root of 37. What is the accuracy of this approximation? So again, we are going to use linear approximation. The formula for it is f of x is roughly L of x, which is f of a plus f prime a times x minus a. So here we need to find out two things. F of x, first of all. So what is f of x? F of x is going to be square root of x, right? Because we want to find square root of 37. We need to also find out a. Now we should choose a whose square root is, so what should we choose for a? So a is chosen to be square root of, a is chosen to be 36. Why? Since we want to find square root of a in our calculation. And a must be close to 37, right? So we are looking for a number which is close to 37 and has a square root, right? Has a proper square root. What do I mean by that? Something whose square root is easy to compute. Yeah. So a is 36. So now let's apply the formula. So we get what? F of a is square root of 36 which is 6. Now we need to find f prime x. So first let's find f prime x, which is going to be derivative of square root of x, which is 1 by 2 root x. This implies f prime at 36. So this is your f of 36, right? Is going to be 1 by 2 times square root of 36, which is 1 by 2 times 6, which is 12. So therefore, we are looking for f of x is roughly equal to L of x, which is f of 36, which is 6, plus f prime of 36, which is 1 by 12, times x minus 36. Now this is a good enough approximation for any x near 36. Our x is what? Our x is equal to 37. Therefore, square root of 37, which is f of 37, is roughly equal to L of 37, which is going to be 6 plus 1 by 12 times 37 minus 36, which is going to be 6 plus 1 by 12, which is going to be 6 times 12 is 72. Sorry, 6 12s are 72. 6 times 12 is 72. 72 plus 1 is 73. 73 over 12. So this is your linear approximation. Now let's see how accurate we are to this approximation. So in this case, I'll use calculator to compute it just to see how accurate we are. So it turns out that this is going to be 6.08333. So this repeating. And what is square root of 37? Square root of 37, if I use my calculator, is 6.08276. So we are accurate up to how many decimal places? We are accurate up to 2 decimal places. That is pretty neat. Yeah. So later on, when we use, we will use concavity to see whether our approximation is an overestimate or an underestimate. The next concept is the idea of differential. So let's try to look at that. So again, suppose we have so you're given the function at some, say this is your function here. So suppose this is your function. At point x, you draw a tangent line. So at this point, let's draw a tangent line. So we have a tangent line at this point. Let the name of the tangent line. So this is going to be the equation of this is going to be L of x, right? Do you agree? Okay. Now, suppose your x changes from x to, so you change from x to x plus delta x. So this is your, so the change in x is, so here delta x, which is equal to dx, be a small change in x. Yeah. So delta x is change in x. Now, how much will your function change? So this is your change in x. So let's see. So this is your original function value. So we have, this is your f of x. And then your function value changes from here to here. So this is going to be your f of x plus delta x. And this difference is called delta y. So let delta x be change in x, then delta y is corresponding change in f of x. That is delta y equals to f of x plus delta x minus f of x. Yeah. Now we want to see if your x changes a little bit, x changes from x to x plus delta x, how much does your y changes? Again, that would be delta y. But instead of doing that, what if we look at the change corresponding to the tangent line? So this would be this change here. Instead of that, the change in the tangent line at x would be dy. This is what is called dy. And this dy is what is called, dy is the differential. So you will say, what are we trying to do? So we are trying to find out delta y, but we approximate it by, instead of looking at change in the function, we are looking at how much does your y value changes on the tangent line. And that is what is called differential. Now, how do we find this differential? So note that this part is your delta x, this part is your dy. So what is the slope of this? So dy over delta x is equal to the slope of the tangent line, which is going to be f prime x, right? Because derivative defines the slope of the tangent line. So derivative at x defines the slope of the tangent line. So you can think about this as dy equals to f prime x delta x. So this is what is the concept of differential. Okay. So dy can also be thought of as L of x plus delta x minus f of x. Now, let's see. So why are we doing this again? One is that it will help us to define the concept of differential, which is useful in seeing small changes in your function, but it will also help you when you're doing integral calculus. Okay. So let's see. So f of a plus delta x is roughly equal to a plus dx, right? Because here, so a plus delta x. So delta x and dx are used the same way. Delta x and dx are the same thing. But delta y is not same as dy. It is approximated by dy, right? Because dy, delta y is here. This change in function, and dy is a change in the change in the y value of the tangent line. So let's see. So if we have a plus delta x, so that means at this point, or x plus delta x or x plus dx, they are the same thing. Then this is f of a plus dx, and that is approximated by this value, which is f of a plus dx. Why? Because this is a linear approximation. Now, if you use the linear approximation on this guy, you'll get f of a plus f prime a plus dx minus a. We are using the linear approximation formula. This is your x, right? Now, if I simplify this, this becomes f of a. This will become f prime of a times a plus dx minus a will become dx. But what is f prime a dx? F prime a dx is f of a plus dy. So what do I get? I get dy equals to f of a plus dx minus f of a. But there's an approximation sign coming from top, so this is approximately this. So this means what? This means that if this guy is small, then your approximation is a good approximation. Okay. So small differential means there's a good approximation. Okay. So that was the whole idea of this discussion. So in other words, you have f of a dx is approximately L of a plus a dx if and only if dy is roughly delta y. So can we look at the following problem now? So the idea is you have an equatorial radius of the Earth is approximately 3960 miles. Suppose a wire is wrapped tightly around the Earth at the equator. Okay. Approximately how much this wire must be lengthened if it is to be strung all the way around the Earth on poles of 10 feet above the ground. So 10 feet, 1 mile is 1760 yards, which is multiply that by 3 to get the feet. Okay, so let's see. What is the question asking us? So you have basically, so this is your Earth, and okay, so now you want basically to, so the Earth, the center of the Earth. So let's draw the equator. So this is your equator, and the radius r is given to you. Yeah. So you are originally basically, so you are trying to increase so the length of the wire which goes around the Earth. So it must be given by a circumference, right? So originally we have R1, the radius or R, to be 3960 miles. And then the circumference formula is 2 pi R, right? Now you are changing your R. How are you changing your R? Basically, you are putting it on 10 feet above the ground. So the idea is you are I know this is not representative of 10, but this is just a rough. Do not scale this, right? So now instead of that, you are increasing this is 10 feet pole. So you're putting a 10 feet pole. So you have 10 feet, putting things on 10 feet pole. So these length of these things are 10 feet pole. So let's see, what is the new radius? The new radius is r plus delta r, and your delta r is 10 feet. So how much, so you are asking how much do we need to increase? How much do we, how much of what? How much of extra wire do we need to wrap it around, right? To basically wrap it around, right? So how much of this wire must be lengthened? That means we are looking for how much extra wire do we need to wrap it on 10 feet pole. So the extra wire would be, so if C is your 2 pi r, then you're looking for delta C. How much does your Y C changes, right? So now delta C is roughly same as what is going to be f prime. So let's call this function C. So C prime at what point? At 3960 times delta x, or delta r in this case, using the concept of differential. So what is C prime? So C prime, again, we are looking at dc by dr. This is going to be 2 pi. So we get this is roughly equal to 2 pi times 10 feet, which is going to be 20 pi feet, which is roughly 62.83 feet. So the wire must be lengthened. Wire must be lengthened by 62.83 feet. And you can do this calculation directly. I mean, this is a simpler case. So let's see, what is delta C? Delta C is change in C. So R1 is, so that is going to be, R1 is, this be R2. So R1 is 3960 miles. R2 is going to be 10 feet. Sorry, miles, 3960 miles plus 10 feet. So delta C is going to be 2 pi R2 minus 2 pi R1, which is going to be 2 pi common, R2 minus R1, which is going to be 2 pi. R2 is what? R2 is same as 3960, or R1 plus delta R, and then R1 is as it is. So this is going to be 2 pi delta R, which is going to be 2 pi times 10, which is 62.83 feet. So you could have done this directly, but this is a linear function, so the differentials are easy. But when you have a complicated function, linearization, the differential is an easy way to compute the change rather than going for delta C or delta Y if your function is y equals to f of x.